For humans, it is very easy to process numeric data. Numbers can be positive, negative, and fractions. If numbers were only positive, it would be a lot easier to represent them in computer memory. We use plus or minus to represent positive and negative numbers. Question is, how do computers show or understand that a number is a positive or negative? Representing positive and negative numbers with plus and minus sign is called signed magnitude representation. First method that we will learn to represent negative numbers is fixed size representation. That is, represent numbers using fixed size of integers where one half is negative of the other half, or one half is positive and other is negative. Take a fixed size of 100 numbers where 0 to 49 can represent positive and 50 to 99 can represent negative. Ignore any carry at third position while adding two numbers. For example, adding 98 and 97, that are two negative representations, will result in 195. So 1 is discarded. So 95 on number line is minus 5. Since 98 and 97 are equal to minus 2 and minus 3 respectively on number line. In binary, easier method is 2's complement to find a negative of any number. To find a negative of a number in binary, invert its bits. That means if there is 1, turn it into 0, and if there is a 0, make it 1. And add 1 to the resulting number after inverting. In binary, often most significant bit shows the sign of number. For example, if most significant bit is 0, number is considered positive. And if most significant bit is 1, number is considered negative. If we assign 7 bits to represent number and 1 bit to represent sign, then representation for 2 will be 0000010, and representation of minus 2 will be inverting bits of 0000010, number becomes 1111101. Now adding 1 to this number, the resulting number becomes 1111110, which is equal to minus 2 on number line to the right side. We can also use formula to find the negative of a number. That formula is 2 power k minus 1, where k represents number of bits used, I is the number. Using the formula negative of I is equal to 2 power k minus 1, we find the negative of 2. Since previously we used 8 bits, here we also use 8 bits. So the negative of 2 will be 2 power 8 minus 2 is equal to 256 minus 2 is equal to 254, which is in binary equal to 7 times 1, 0. This is same result we got in 2's complement with binary numbers. Sometimes while performing operations, there might arise a situation where a calculated value cannot fit into the number of digits reserved for it. This condition is called overflow. Representing numbers with only 8 bits will not be enough for some values. For example, with 8-bit representation, adding 127 to 3 results in 130 in actual result. But that is 130 is equal to 100000010, and this number is equal to minus 126 on number line. So computer will give you a wrong result for this operation. For whole numbers, we employed division method for conversion in binary. A real number has two parts: whole part to left of dot and fractional part right of dot. Fractional part is converted to binary with multiplication by 2. Whole part is converted with same division method discussed in earlier lectures. Fractional part is multiplied again and again, and carry to left of dot is next digit to the right in result. Here we, for an example, here we convert 0.729 into binary. Multiply 0.729 by 2. Result is 1.458. So the 1 will be next digit to the right in result. And fractional part is 0.4458. Fractional part will be multiplied again. So the result is 0.916. Now 0 is next digit to right in result. Again 0.961916 is multiplied, and the process continues in this way. Text is composed of alphabet characters, lowercase and uppercase letters, symbols for numbers, punctuation marks, symbols related to currencies and other fields. Besides English alphabet letters, there are many other languages that have different characters and need to be represented in computer memory. To represent in computer memory, all characters are listed and assigned a string of binary digits to each one. For this purpose, different coding systems have been devised to represent every character with bit string. Number of bits assigned to each character depends on the number of characters we want to represent with a specific coding system. Character set is a list of characters and binary codes used to represent each character. Different number of character sets were active in earlier computers. IBM alone used 9 different character sets in different machines in 1960s. To make processing of text data easier, computer manufacturers agreed to use one character set in all machines. We will discuss two of these character sets here, ASCII and Unicode. ASCII stands for American Standard Code for Information Interchange. First version of ASCII used 7 bits to represent a character. It provided representation for 128 characters. Eighth digit or bit was check bit that was used for accurate data transmission. ASCII evolved to use 8 bits and named as Latin 1 extended ASCII character set. It provided representation for 256 characters. Codes are given to characters in sequence. Codes for uppercase alphabet start from 65 and lowercase alphabet start from 97. With 8 bits, ASCII could only represent characters of English alphabet. To represent characters of every language and special purpose symbols, a 16-bit coding system called Unicode was introduced. Two factors paved way for a new coding system: 16-bit computer architecture and introduction of World Wide Web. Unicode is superset of ASCII. First 256 characters of Unicode are same as ASCII with same binary codes. So program that had ASCII as character set will not be affected on the system that uses Unicode.